All right, so we just did graphing the derivatives. Now we're going to talk about differentiability. So I'm going to review these two formulas. I'm going to write them out again. I suggest you do too. Oh, I'm sorry. I can see it just fine. There you go. Sorry. I'm going to write them out, and I'm going to encourage you to do it too. I mean, if you want to dig your heels in and be like, but Miss Cole, I have it written somewhere else, then, fine. But I want to illustrate the difference between them as well. The derivative at any point, like where you just get a formula with an x in it, limit as h goes to 0, f of x plus h minus f of x all over h. That's good if you want the derivative at lots of different values. Like you want to plug in 1, plug in 2, plug in 3. You have a formula for it. If you just want the derivative at one specific point, you can kind of bypass that. Its limit as x goes to c, c being that value that you want the derivative at, f of x minus f of c over x minus c. And just remember, these are slopes. Like that's what it all boils down to. However complicated it gets, at the end, it's slope. So when this says find f prime of 2, would we want the first formula or the second formula? If we just want f prime of 2. Good, the second one. All right, it's going to take us straight to the answer. So it'll be limit as x goes to 2. And then it says f of x. So, okay, the function minus f of c, and c is 2. So we're going to plug 2 into this and see what we get. All right, 2 squared is 4, times 3 will be 12, plus 2 will be 14. And then over x minus 2. Spoiler alert, it's going to be indeterminate. You're going to have to factor this. All right, so bring your limit notation with you. We have to get something to cancel out. So that's going to be 3x and 1x. 14 would be 7. Let's see, we want positive 7 and then minus 6 for the outsides. One of them was going to have to be an x minus 2 because this is going to have to cancel out. And if you don't write the limit, you're probably going to forget to plug in 2. So just make sure you write the limit. It's not that long of a problem. This is a 2-step problem. Now we're going to plug in 2 and get our answer. So that'll be 6 plus 7, 13. So the derivative, f prime of 2, derivative at 2 is 13. Slope of the tangent line, instantaneous rate of change. So I was just reviewing how to use that formula because we're going to need it down here as well. So 8, I'm giving you a piecewise function. Is the function continuous at 3? All you need to check is, do the two pieces meet up at 3? So you're going to plug 3 into both of them and see if it comes out to the same thing. So if you plug 3 into the first piece of the function, what's that going to give you? Good, 7. And if you plug 3 into the second piece of the function, 7, hooray, it's continuous. But is it differentiable? Now that means the derivatives from each side need to meet up. So we're going to do this problem from the left and from the right, right? So limit as x goes to 3 from the left, we're going to use the first piece of the function, the part smaller than 3. So it's going to be the function x squared minus 2 minus f of c. We already did it, it's 7. And then over x minus 3. Spoiler alert, it's going to be 0 over 0. You're going to have to get something to factor and cancel out. So that numerator is really x squared minus 9. So how's that going to split? X plus 3, x minus 3, difference of squares. I hope there's enough 3's in this problem for you, like everywhere. X minus 3's cancel, and then you plug in 3. Again, if you don't write the limit, you're probably going to forget to do that. But Miss Cole, it's 3 from the left. That's fine. You're still just plugging in 3. 3 plus 3 is 6. So the slope from the left is 6. And then we're going to do the slope from the right. So limit as x goes to 3 from the right. Now we're going to use the other piece of the function. So it's 2x plus 1 minus f of c, which again, we did it already, it's 7, and then over x minus 3. So you're going to have to get something to cancel. That numerator is really 2x minus 6. So what can we do with that? It's 2x minus 6. Yeah, good. Take out 2. You'll be left with x minus 3, which you're going to cancel. And so you just get 2, which should actually make sense. And you could have actually done that without doing any work because the slope, that's linear. So the slope is 2. But I wanted you to practice doing that again. So that's why I did that. Anyway, yes or no, is it differentiable? No, because the slopes did not match up. So what's going on there is you have a parabola and then a line. So you have, a parabola and then it meets up with a line and you get that sharp edge there. So that's why it didn't work out. All right, a function is differentiable if. So these are the rules. You can have no discontinuities. No discontinuities. Function has to be continuous. So discontinuities would be things like holes and asymptotes and jumps. Or you can have a hole and then the point be somewhere else, all those things. All right, no sharp edges. Some people want to get like nitty gritty into the vocabulary. This is a corner and this is a cusp. That's a corner and that's a cusp. I tell everybody just say sharp edge and then you'll be good no matter what. No sharp edges. People usually remember these. You might even remember them from last year. Seem familiar? Everyone always forgets the last one for some reason. I don't know what that is, but it is no vertical tangent lines, which would look something like this, where you get the graph to go vertical in the middle. The reason why is, well, here, let me ask you, what is the slope of a vertical line? Yeah, like by definition, you can't get an answer, which is maybe why people forget that one because it's just like, well, there's an answer. So we're going to look at these ones on the back and discuss the continuity. Oh, I want to write out real quick though. If a function is differentiable, and from now on, I'm going to abbreviate differentiable, diff, and continuous as con. Is that okay with everybody? I get that they're long words. If a function is differentiable, then it is continuous. If they tell you a function is differentiable, it's automatically continuous. So you can't have any discontinuity. That comes up a lot on the AP exam because they'll tell you, oh, blah, blah, blah is differentiable, and then ask you to prove something, and you have to be like, oh, well, the function's also continuous. But if a function is continuous, it is not necessarily differentiable. It might be, but it might not be. So if you're only told that it's continuous, you don't get to assume that it's differentiable. Do you see how it's like all, what is it? All squares are rectangles, but not all rectangles are squares. I hope I said that the correct direction because my brain's a little fried right now. Okay. All squares are rectangles, not all rectangles are squares. All right, so we're going to discuss the continuity and differentiability. It sounds like, those are such big words. It sounds like we're doing something like really great. It's actually like not that big of a deal. Number 9, is the function continuous or not? What do you think? Yeah, it's continuous. So continuous for all real numbers. Is it differentiable all the time? No. So where is it not differentiable? At 0, yeah, good. Not differentiable at x equals 0 due to sharp edge. I'll take abbreviations. Yeah, and on the AP exam, they will too, unless you over abbreviate to the point where they can't tell what you're talking about. Like if you just wrote D, I don't think they would take that as differentiable, or C, like I don't think they would. But I mean, as long as they can tell, and the at symbol, they'll take that. They'll take all of that. Like when we get into the theorems, intermediate value theorems, like IVT, mean value theorem, MVT, they'll take all of them. All right, number 10, is this function continuous? No, we are not continuous at x equals 2, I'm going to use the formal notation because f of 2 does not exist. Because sometimes they won't take it if you just write asymptote. Like they want the formal like notation definition, which is actually shorter than spelling out asymptote, to be honest. And then we're not going to be differentiable for the exact same reason. Not differentiable at x equals 2 because f of 2 does not exist. This is the exact same reason. All right, how about 11? I threw an easier one at you. What do you think? It's continuous and differentiable. Yeah, don't worry. I'm not going to like yank you out in the hall like in language classes and make you take like a verbal exam. All right, and then 12 is continuous all the time, but not differentiable at x equals -3 due to sharp edge. I'm letting us just write due to sharp edge there. Occasionally, I have seen this on free response questions. They want you to actually work this out, like I showed you right here. Find the derivative from one side, find the derivative from the other side, and show that they're not the same. I've taught you that. You would just have to do this. But they would give you an actual function. I just like put a picture on it. Do you guys get what I'm saying? Like they would make you work it out with the limits. And then I like this last one. You have to put them in order. We want to identify f prime, and f double prime. So it's like a first derivative and then a second derivative. Basically, it's the most wiggly to the least wiggly. Because again, you're going to go down a degree every time. So which one do you think is f, the original function? C, do you see how we have a critical point here and here? So now you want the derivative of C. That's going to be the graph that has zeros here. And I'm sorry I'm saying here and here, but the axis isn't labeled. So which one would that be? That'll be B. Do you see how B has x-intercepts there? Like they match up. And then B has a critical point right here. And do you see how A matches up with that? So you're putting them in order. I like that question.